Okay, let's look at convergence and divergence test using the direct comparison. Now, when with the direct comparison, when the series is given, you compare it to a known series, a known series, and normally we compare it to the geometric series or the P series. We normally compare it to a G series or a P series. Good, good. So what you do is that you modify the given series in the form of either a geometric or a P series. Whether you are going to choose a geometric or a P series will determine on your understanding of a GP and a P series. Good. Let's look at the P series and the what do you call it? The P series and the geometric series. Because the nature of the series given will determine whether we should compare it to a G series or a P series. Now, we'll come back to the previous screen and look at certain tips there. A P series is always of the form 1 over n power p. And by the P series, if the value of p is greater than 1, then the series will converge. Good. Then the geometric series, so this P series. Then there is a G series. The G series is always of the form AR power n minus 1. It's like a geometric progression. Or it can just be AR raised to the power n. And when your R, which is the common ratio, the absolute value of the R, which is the common ratio, is less than 1, then we say the series converges. When this is the absolute value of R is less than 1, then the series converges. The series converges. The significant difference between the P series and the G series is the position of your n. In the P series, the n is the base. The n is the base. Whereas in the G series, the n is the exponent. So when the series is given and you want to modify it to look like either a G or a P series, you should look at the position of the n. If the n is the base, then you have to compare it to what? A P series. But if the n is an exponent, then it should be compared to a geometric progression or a G series. Good. In comparing, we should determine whether your modified version is bigger or smaller than the original. For example, if the original is AN and your modified version should be BN, you should determine whether it is bigger or smaller. In a case where your modified version is bigger, so for example, AN will be lesser than BN, that means your modified version is bigger. You can only test for what? Convergence. You use convergence to determine whether you test for convergence, whether this be your modified version converge. If it converges, then the original will also converge. When the modified version is bigger, you cannot use that one to determine divergence. Now, when your modified version is rather smaller than the original, then in this case, we'll test for divergence. So we test whether our Bn diverges. When it diverges, we will say that our An also diverges. That means when our modified version is smaller, it can only be used to determine divergence and not convergence. Good. How do you determine whether the modified version is bigger or smaller? You should take note of this. If I have a fraction, 1 over, let's say, 10, and I have another fraction, 1 over 10 plus 5, a third fraction, 1 over 10 minus 5. To test which of these fractions is the biggest, we look at the denominator. When the numerators are the same, we consider the denominator. The moment the denominator is bigger, as long as the denominator is increasing, the fraction becomes smaller and smaller. What it actually means is that if I have 1 over 10 and I have 1 over 10 plus 5, otherwise 1 over 15, 1 over 15 will be smaller. Smaller compared to this one. So smaller than this. Because you have 10 people sharing one item. And then 15 people sharing the same one item. You see that the portion that each person will get when they are 15 will be smaller than when they are 10. Then we have another one. 10 minus 5. 1 over 10 minus 5, or otherwise 1 over 5. This fraction is bigger compared to this one. It's bigger because the denominator is smaller. It's like 5 people sharing one item. What they will receive will definitely be bigger than when 10 people are sharing the same item. So when the denominator are the same, I want to compare the bigger fraction. You look at the denominator. The bigger the denominator, the smaller the fraction. Good. Let's go back and reset in rules. So in the direct comparison test, you'll be given An as the series. Then you modify it and get a Bn. And the Bn can be a P series or a G series, depending on the original. Then when your Bn is bigger, you test for convergence. So if the Bn converges, is bigger and converges, then the original will also converge. Now, if your Bn is smaller than An, the original one, then you can only test for what? Divergence. So if the Bn diverges, the An will also diverge. Take note of this. I want to repeat that again and stressed. If the Bn is bigger, the modified version is bigger, you cannot use that to determine the divergence of the original. You can use that to determine the convergence of the original. So even if the Bn diverges, you can't conclude that the An also diverges. No. It is only and if only the Bn converges, then you can say the An also converges. The bigger one, the modified bigger one converges, then you can say the An also converges. When it comes to the modified version where it is smaller, when it's smaller, we can only draw conclusion and say that when the Bn, the modified version which is smaller, diverges, then the An or the original one, will also converge. What it means is that if the smaller one in this case, which is the modified one, converges, it is inconclusive to say that the AN also converges. It is only when the smaller one converges, then we can say that the original one, which is bigger, converges. Based on this, let's look at some question. We'll look at this question. But we want to find out whether this series converges or diverges. So we have to create a modified version of this series. Now, you ask yourself, which modified version are you going to create? Is it a P series or a G series? Remember, I said the significant and unique thing about the P series is that the N is the base of the index, the expression, the index. When the index is given, the N is always the base. But when it comes to the geometric progression, the N will be in the position as a power. So when we come here, you can see the N is the power of this expression. So this is a gene series. This can be compared to a gene series. So let's create a gene series out of this. Good. Now, we can create a gene series by rewriting this as what? 5 power n over 9 over n, ignoring the 4. Ignoring the 4. And this can be rewritten as 5 over 9 all power n. All power n. Then we compare this one to the original. Which one is bigger? We are going to use the ideology that we stated here. When the denominator is bigger, then the fraction is smaller. The bigger the denominator, the fraction is smaller. So let's come here in the original and this one. Which one has a bigger denominator? The numerators are the same, 5 raised to the power n. 5 raised to the power n, 5 raised to the power n. So we ignore. Let's go to the denominator. Which has a bigger denominator? The original one is 9 raised to the power n plus another figure 4. And this one is 9 raised to the power n. 9 raised to the power n. So it implies that the original one has a bigger denominator, and that fraction in the whole will be smaller. In that case, we can say the summation of 5 exponent n over 9 exponent n plus 4 from n is equal to 1 up to infinity is lesser than our modified version, summation 5 over 9 all raised to the power n from n is equal to 1 up to what? Infinity. Good. Since our modified version is bigger, we can only test for convergence. Now, then we look at the property of a gene series because this is a geometric progression. Under what condition will a geometric progression converges? It is only when the absolute value of the common ratio is less than 1. So here our common ratio is what? 5 over 9. 5 over 9. And since 5 over 9 is less than 1, we can conclude that summation 5 over 9 power n from n is equal to 1 up to infinity converges. And if this converges, then the original one will also what? Converge. The original one will also converge. Good. Let's look at another one. This is 4 root n over cube root of n squared minus 1. Good. Should we compare this to a P series, or we should compare it to a G series? You can pause the video and test and ask yourself, will you compare it to a P series or a G series? Remember, the P series, n is always the base, and the G series, the n is always the exponent. So in this instance, we can see the n is the base of the expression. So hence, we have to compare this one to a P series. Good, good. So we'll create a modified P series from this. And this will be summation 4 root n over the cube root of n squared. Summation 4 root n over the cube root of n squared. Good. Now, we can simplify the expression further and then try to determine the value of our P, because the value of the P will determine whether our series, the new modified version, converges or diverges. But before then, let's ask ourselves, which of this is bigger? Is the modified one or the original one? We can see that in the original one, we have -1. And then the only difference between the original one and the modified one is that in the original one, we have -1. It means the denominator in the original one is going to be smaller than the denominator of the modified one, just by a difference of 1. So in that instance, this fraction is going to be bigger because it has a smaller denominator than this. So our modified version is smaller than the original one. Because the denominator here is bigger, meaning bigger denominator means smaller fraction. So the whole expression here is smaller than the original one. And remember the comparison test. If it's smaller, we test for divergence. If the expression converges, then we cannot use, it's inconclusive. You can't conclude that the original one also would converge. No. So far as it is smaller, we can only test for convergence, divergence and conclude. Okay. Now, so here we are going to simplify this and then test for divergence, whether the modified version diverges. When it diverges, then the original will also what? Diverge. If it converges, it is inconclusive. Take note. Because for it to use convergence, the modified version should be bigger than the original one. Good. Now let's simplify this expression further. So sigma 4 into brackets. I've just taken the 4 out. N raised to the power half over n squared raised to the power 1/3. And this becomes 4 n raised to the power half over n 2 over 3. 2 on 3. So we are going to have sigma 4. Remember, if we have in indices, when two fractions are dividing, we just subtract the exponent. So to divide this, we can just subtract the powers. So half minus 2 over 3, or 2 on 3. Half minus 2 on 3 will give us negative 1 over 6. So this becomes n raised to the power negative 1 over 6, which can be rewritten as 4 1 over n raised to the power positive 1 over 6. Positive 1 over 6. We have gotten our P series. And we know that this one is lesser. So we can write this statement as the summation for into brackets 1 over n power 1 on 6 is lesser than the original one, summation 4 root n 4 root n over the cube root of n squared over the cube root of n squared minus 1 minus 1. Then, since this is lesser, the modified version is lesser. We'll test for what? Whether it is it diverges. And for a P series to diverge, then the P should be less than 1, less or equal to 1. If it should diverge, it should be less or equal to 1. For a P series to diverge, it should be less or equal to 1. If it is greater than 1, it converges. But we are not going to test for convergence here, because even if this expression converges, it is inconclusive in this scenario because it is a lesser series. Good. Let me write the notation well from n is equal to 1 up to infinity. N is equal to 1 from n equal to 1 up towards infinity. Good. What is the value of P in this expression? Our value of P is equal to 1 over 6. And since 1 over 6 is less than 1, we can conclude that the summation for 1 over n power 1 over 6 from n is equal to 1 to infinity diverges. And since the modified smaller series diverges, we can also conclude that the original one also diverges. Thank you very much for watching.